Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the second module of NPTEL course on earthquake seismology. Today we are having lecture 1 of module 2. In this lecture we will be talking about wave number vector, slowness vector, P and S wave polarization. So the concept that we are going to cover today will be the wave number vector, slowness vector, P and S wave polarization, and then we will provide a summarized form of the today's lecture. So as far as the wave number is concerned, it is represented by k, and because it is a vector, so it is k vector, and in 2D where the coordinate axes are x1 and x2, then the k vector can be written as k1 e1 cap and k2 e2 cap. E1 and E2 are the unit normal vector along x1 direction and x2 directions respectively. So the modulus of the k vector would be under root of k1 square plus k2 square, that is in 2D. Similarly, you can write the wave number vector in 3D as well. That will be having the additional term in x3 direction. So that will become k1 e1 cap, k2 e2 cap plus k3 e3 cap. So similar to 2D case, we can also write its modulus, that is k1 by k vector modulus is equal to under root of k1 square plus k2 square plus k3 square. Now when we would like to write the wave number vector in terms of its unit vector, then it will be simply the product of its modulus and its unit normal vector. So k vector will be equal to modulus of k vector, and that will be multiplied by its unit vector. I am sorry, I did say the normal vector, it should not be normal, so it will be normal vector, it should be only the unit vector. So the wave number vector basically tells us about the path a wave is propagating through, so it will always be along the direction of the propagation of the wave. So all in all, we can write the modulus of k vector will be equal to under root of k1 square plus k2 square plus k3 square, that will be equal to omega by alpha, where omega is the angular frequency of the wave and alpha is the p wave velocity. So we can write that k vector will be equal to modulus of k vector multiplied to the k unit vector, that will be equal to omega by alpha k cap. This cap should be here. So if suppose we want to define a plane wave solution in terms of the potential field, then the scalar potential phi x comma t is equal to a e to the power minus omega iota in bracket omega t minus k vector dot x vector, where x vector is the position vector, and this phi x comma t is your scalar potential, it is not the displacement. And if suppose this amplitude is a function of angular frequency, then we can probably rewrite this scalar potential equation something like this, that is phi x comma t is equal to a, that is a function of omega e to the power minus iota omega t minus k vector dot x vector. So the slowness, if we define, the slowness is basically the reciprocal of the velocity, and s vector, it is represented by s. So because it is a vector quantity, so we can write it s vector, that will be equal to s cap divided by some arbitrary velocity c, and that will further be equal to s cap by velocity. And for p wave, if you want to write, then it will be s cap divided by alpha. So here c is the arbitrary velocity and alpha is the p wave velocity. So in terms of, so we want to define the wave number vector in terms of slowness vector. So what we can write, k vector is equal to basically the omega by alpha k cap. So this omega by alpha, 1 by alpha is your modulus of slowness vector. So we can replace that with s, modulus of s. So k vector will be equal to omega modulus of s k cap, and this, so where s this should not be there, so this will be modulus of s is equal to 1 by alpha. So direction of s cap and k cap will be same, so k vector will be equal to omega s vector. So this will become this, so because modulus of s into k cap will be your s vector, as I said, like k cap will be having the same direction as that of s cap, so both will be the same thing. So it will basically help us to rewrite the potential in terms of slowness vector. So the potential equation, the equation of potential will become in terms of slowness vector something like this: phi x comma t will be equal to a omega e to the power minus iota omega t minus k vector dot x vector, that will be equal to a omega e to the power minus iota, so iota in bracket omega t minus k will be replaced by omega s vector dot x vector. Now we can take omega out of the bracket, so it will become a omega e to the power minus iota omega in bracket t minus s vector dot x vector. So similarly we can write the equation for s wave. S wave potential can be written as, this is your psi vector is equal to x vector comma t. X is the position vector, that will be equal to b omega, that is the amplitude of the shear wave, that is a function of omega. Again we did this is basically the same thing as previously we have done, that will be e to the power minus iota omega t minus omega s vector dot x vector. So now if we take omega common, then it will become b omega e to the power minus iota omega in bracket t minus s vector dot x vector, and here this k vector will be equal to omega by beta. So here instead of alpha we are taking beta because we are talking about shear wave. So this beta is shear wave velocity into k cap. This should be basically k vector, a small k vector instead of capital K vector. Now let's talk about what is polarization of P wave and S wave. So when we are talking about the particles of the earth in which they are moving as the seismic wave is passing by, so what we are basically doing, we are trying to find out the displacement of the particles or displacement of the seismic wave. So to basically find the displacement or the particle motion of the material from which the wave is passing by, we can find it using the potential function. So let's suppose the scalar potential for P wave is phi and scalar and vector potential for shear wave is psi. Then we can find out the displacement for P wave, that will be represented by u in subscript p vector, that will be equal to gradient of phi, that is a scalar potential function. And for S wave we can similarly find out us vector, that is the displacement for the shear wave, that will be equal to the curl of psi. Now let's suppose the P wave is traveling in x direction. The P wave potential equation may be written as something like this: del square psi minus 1 by alpha square in bracket del square psi by del t square, that is equal to 0. Since P wave, this P wave is not traveling in y and z direction, so the general solution that you can take for the potential, scalar potential, that will be psi as a function of t plus minus x by alpha, and we can also denote this psi as a sum of the P wave traveling in positive x direction and the negative x direction, and then we can write psi is equal to psi 1 as a function of t minus x by alpha plus psi 2 as a function of t plus x by alpha. So you can see this is your positive x direction wave, this is your negative x direction wave. So if you want to define the displacement or the particle motion of this p wave, and you can use this phi, you can take the gradient of the phi. When you take the gradient of the phi, then what you will see, you will get del by del x phi, del by phi, and del by del z x of phi, and that is similar to this del phi by del x, del phi by del by, and del phi by del z. So now, since I have said the scalar potential and the wave is traveling in only in x direction, so these two functions del phi by del y and del phi by del z will become 0, and then you will only be left with del phi by del x comma 0 comma 0. That means you are having your displacement only along the x direction, that which basically say that for a p wave traveling in x direction, the particle motion or the displacement will be in the direction of the propagation of the wave. So the p wave moving along x direction, that is the p wave that we took. If we take del phi by del x, if suppose your p wave along the x direction is something like this, then if you take del phi by del x, then it will become something like this. That means your displacement vector will become minus iota kx phi. The kx is the wave number along x direction, because wave is traveling in x direction only, comma 0 comma 0. So only the thing non-zero component that you are getting in x direction. So which means for p wave, particle motion is in the direction of the propagation. Similarly, you can perform such operations for S wave in case you want to find out the displacement of the shear wave, or you can say the particle motion of the shear wave. So let's define the equation, the scalar, so let's define the vector potential equation for p wave. This is the differential equation that you have, del square psi minus 1 by beta square in bracket del square psi by del t square, that is equal to 0. Let's consider an arbitrary S wave vector potential. So let's suppose this vector potential along all three directions is psi x, comma psi by, comma psi z. Let's assume it is traveling only along the x-axis. Then the k vector for shear wave will be having component only along the x direction. The other two component will be 0. So it will be k, comma 0, comma 0. So the psi x, comma t will be equal to b omega e to the power iota minus omega t minus kx. So this was basically your k vector dot x vector. So basically the position vector only will be having the component in the x direction, and k vector will be having only component in the x direction, since the wave is traveling in x direction only. So finally what you will get, kxx. So b omega iota minus omega iota in bracket omega t minus kxx. So since the S wave is traveling in x direction, so potential will be a function of x. Then the psi x will be psi x t minus x by beta, psi y is equal to psi y t minus x by beta, and psi z will also be a function of x, because the wave is traveling only in x direction. So now if we compute the displacement, that will be your u vector, that is your displacement, will be the curl of the psi, that is your vector potential of shear wave. So that you can solve it using this metric form, x cap, y cap, z cap in the first row. That will be your del by del x, del by del y, del by del z, and that is the psi x, psi y, and psi z. When you will solve it, it will look something like this. So basically, since you know the psi y, psi x, and psi z all are function of x only, so the terms are like yz by del y and del psi x by del z and del psi x by del y and say del psi y by del z will become 0. So as I told you, like psi x and comma psi y and also psi z are function of x only. So basically, if you take its partial derivative in other direction apart from x will become 0. So that is what it is happening. All these components are basically the partial derivative in other direction apart from x. That's why they all are becoming 0 here. So now when we incorporate these zeros into this particular equation for the displacement vector, then what you will get? You will get something like this, where this term entirely will become 0, and here you only will be having this term left, and in this here you will be only having this term left. So this is what it is written: u vector is equal to x cap 0 plus y cap minus del psi z by del x plus z cap del psi y by del x. So u vector will only be left with two components that will be along y direction and z direction. So basically you can say, all in all, the S-wave particle motion is purely in the direction perpendicular to the wave. So your wave was traveling in x direction, but your particle motion is in the perpendicular direction to the propagation of the wave in case of shear wave. Now the shear wave has two components. One is SH wave, another is SV wave. So SH wave is basically the shear wave that is polarized in horizontal direction. Similarly, the SV wave is basically the shear wave that is polarized in station receiver plane. So whenever you see the S wave field, then it will always be associated with SH wave and SV wave. And this SH wave is polarized in horizontal direction, and SV wave is polarized in the plane of station and receiver plane. So if you look at this particular diagram, this one and this one, then you can see there is this source here, there is this source here, and there is this receiver on the surface. And you can see the ray is traveling from here to the surface, and there are some wavefronts that are basically forming here, and this ray is perpendicular to the wavefront all the way towards the station. So this is basically representing the bending of the ray path. And when we will talk about, we will say, let's suppose if this is a shear wave, then it will be having two components, SV and SH. So when this ray is traveling towards the station, then you can see there will be a plane, this plane, which is basically the plane of station and the receiver plane, or you can say the source and the receiver plane. And this plane that you are seeing, that is here, this basically this one, you can see this plane here. This plane is basically the plane in the SH wave motion. So you can see as the wave is bending, this plane is also bending, but the SV wave motion is always perpendicular to this particular plane. Likewise, the SH wave motion is horizontal to the surface. So you can see this here, this is the surface on the top, and this horizontal motion is always parallel to this surface. So you can say the SH wave or shear wave is always parallel to the surface, and SV wave is always perpendicular to the plane that joins the source and the receiver. So what thing that we can note today is that SV wave is always perpendicular to the propagation direction and in the vertical plane containing the ray path. So let's suppose this is your shear wave that is traveling in the x direction, and this is your y direction, this is your z direction. So this is the x direction along with the shear wave is traveling, and shear wave has two components. One is SH wave motion, another is the SV wave motion. So this will be your SH wave motion, and here you will be having the SV wave motion. So as far as the summary of today's lecture concerned, we have talked about wave number. The wave number vector shows the direction of propagation. and it is represented by a small k. I am sorry, it should not be capital K. Here also it should be small k. So k vector is equal to modulus of k vector, k unit vector, is equal to omega by alpha k cap. Slowness vector has the direction same as wave number vector, that is s vector, that is equal to s cap by arbitrary velocity, that will be equal to s cap by alpha in case of p wave, that can also be equal to s cap by beta in case of shear wave. And slowness vector in terms of the wave number vector can be written k vector is equal to omega modulus of s k cap. Since k cap has similar direction as that of the s cap, so this can further be equal to omega s vector. The particle motion of p wave is parallel to the wave number vector. So that is that we have already derived. So the wave number, so the displacement vector for p wave was equal to minus iota kx scalar potential for p wave, comma 0, comma 0. So here only the non-zero term is in the x direction where the wave is traveling. So we can say the particle motion of p wave or the displacement of the p wave is always in the direction of the propagation of the p wave. Similarly for s wave, the particle motion or the displacement of s wave is perpendicular to the propagation of the s wave or the wave number vector of the s wave. So you can see, like, we have derived the displacement vector for s wave that was having non-zero component in the direction perpendicular to the propagation of the wave. If suppose the shear wave is traveling in x direction, then the displacement vector will be 0 for the x direction, but it will be non-zero for other two directions. So that means the shear wave particle motion is perpendicular to the propagation of shear wave. So these are the references, and this is all for today's lecture. In today's lecture, we learned about wave number vector, slowness vector, particle motion of p and s wave, and also learned about the decomposition of shear wave. That means it has two components, shear wave, sh wave motion and sv wave motion. And in the next lecture, we will talk about further into module 2. Thank you so much. Bye-bye.